We used the categorical distribution to model more possible states of the weather. We encoded them with integer values 0, 1, and 2. A probability mass function was given by the help of the indicator function, but we needed some sort of a value theta. How can we defer this value from an observation set of possible states? And here we need the maximum likelihood estimate. Hi, welcome to a new video. Today I want to derive the maximum likelihood estimate for the categorical distribution, and in the end we will check our derivations with the help of TensorFlow Probability. So as said in the intro, we have an observation set or a data set of days where we observed different states of the weather. So for instance, 2 days with cloudy weather, then we had some days with rainy weather and sunny and so on. And we want to know what the probability is that we observe a certain state of the weather, and we want to defer this from the data set. And we use the maximum likelihood estimate, so we choose those parameters theta that maximize the likelihood of our data set. For this, we first have to define the likelihood. And the likelihood was given as the probability of the data set. So we also denoted this with a capital L of the data set, and we put in our theta parameter, as this is like a parameter to the likelihood, and we want to vary this theta parameter in order to maximize likelihood. And we assume we have an IID dataset so that we can take the product over all the samples. So we take the product from 0 to our n-1th observation, and we check how likely this observation, or how the probability of this observation is. And if we plug this into our probability mass function, then we see we get a double product, the product over all the samples, and then we get the product over all possible states. And here we have theta d, so the dth entry of our theta vector. In our case, our theta vector only has 3 entries, and we raise this to the indicator function that the ith weather observation equals the d state associated with those theta value. Okay, similar to other derivations, it's usually easier to work in terms of the log likelihood. So we derive the log likelihood. For this, we just apply the logarithm operator to our likelihood, and we denote this with a small l. And again, based on our data set and the parameter vector theta, and we apply the logarithm to our full likelihood. And if we apply the logarithm first, then a logarithm turns a product into a sum. Then our operator propagates, then again it turns it into a sum, and then it propagates, and then by the logarithm rules, an exponent is put down in front of the logarithm, and we are left with the logarithm of theta d. So what we get is we have the summation over all our samples, then the summation over all our states, times the indicator function that we observe the ith weather state to be the d state, so that the ith weather observation is, for instance, d. If d is 0, then for instance it is cloudy, and times the logarithm of theta d. Then we can define the maximum likelihood estimate, or shorthand MLE. And this will be, so we say that the theta parameter that we're looking for, the optimum or the maximum with a star, is given as the arc maximum over all thetas. And what is the range that we can take? So each theta is a probability, so it has to be in the range from 0 to 1. So we have a vector which is in the range 0, 1 in each of its components. So we raise this to the power of d. It will be a d-dimensional vector with components being in the range from 0 to 1, and they can take any value in between those two. And we want to maximize the log likelihood, so we apply our argmax operator to the log likelihood of the dataset given the parameter vector. And we have one really important constraint, which we also looked at in the introduction of the categorical distribution, and this is that the summation of the parameter vector, or the reduction of the parameter vector, has to add up to 1. And now we have some sort of a constraint optimization. So let's call this the constraint optimization. And to solve this constraint optimization, we have to use some sort of a trick. And in mathematics, there is a way to incorporate the constraints into our target function or in our loss function. And that's what we have to do. So incorporate constraints into target function. And the way we do this, because we have an equality constraint, we can use the Lagrange multipliers. Or we can use a Lagrange multiplier because we only need one. So a Lagrange multiplier. How does a Lagrange multiplier work? So we define a constraint function by looking at our constraint and rearranging it so that that 0 is on one side of the equation and all of it is left on the other side. So we have the sum from d is 0 to capital D minus 1 over theta d minus 1 is 0. And we define this as our g of theta vector as the constraint function. And then we can define our augmented target. And the augmented target, we call this L hat, which is based on our data set, or it's the augmented log likelihood based on our data set, and the theta vector, and a Lagrange multiplier lambda. And it is given as the original log likelihood that is based on the theta plus lambda times the Lagrange multiplier. And for convenience, I will rearrange this. So this is equivalent to 1 minus the sum of d0 to capital D minus 1 in order to have like a little easier notation. And if we then plug in what we have, then we get for the log likelihood the double sum first over our data set, then over all the states. And then we plug in the indicator function of the ith observation being the dth state times the logarithm of theta d plus of course we take the brackets in order to say that these two sums only apply on this component here. And then we have lambda times our constraint, which is 1 minus the summation from d0 to d minus 1 of theta d. Okay, now we have an unconstrained optimization problem, and we can take the classical strategy of taking the derivative and setting it to 0. So I will note this down because the next steps will be a little complicated. So we take derivative and set to 0. Okay, let's do this. Let's take the derivative of L hat with respect to theta. But we don't want to take it with respect to the full vector. We can take it with respect to only one component of the vector. So this will be theta e is one component of the theta vector. And be aware, this like theta e, this is another like index that I introduce here in order to denote this. And we will quickly see what it like does with our term here. Okay, so derive with respect to theta e. We first go over, or our derivative is going over the first summation, then over the second summation, and then it would apply to the product of the indicator times the logarithm of theta d. And the indicator does not contain any theta e, so this is just ignored. But the logarithm of theta d, since we have a summation that is going from d0 to d capital D minus 1, at a certain point in the summation, it will take the value e, and then we will have a theta e. And in this case, we would take the derivative and it would actually output a value. In the other cases, so for instance, let's say e would be 1 and we would have a theta 0, then the theta 0 is just a constant in terms of the derivation with respect to theta 1. So we can ignore it in a sense where it's like it turns out to be 0. So in essence, this means that the sum that we have here is just reducing into one component. And this is the component with e. So we can just replace anything with d by e. So we have the summation over the data set again. So overall our n observations. And then we have the indicator function that our I of observation is the Eve state times, and then we have to take the actual derivative. So in this case, we will have the derivative of logarithm of theta e with respect to theta e, and this will be 1 over theta e. And then we take the brackets again in order to say like this sum is only applying to this term, plus, and here's the same game. So at a certain point in the summation, the d will be the value e, and then only this component will be relevant because all the others will derive to 0. The 1, of course, also derives to 0. It's a constant with respect to theta e, and we are left with a minus 1 because theta e with respect to theta e is 1, and we will then have a minus lambda. And we can then rearrange this a little bit and say this is nothing else. So okay, also of course, let us denote that this has to be 0. And this will then mean that lambda is, well, theta e is a constant in terms of the summation over I. So we will have theta e times the summation from I0 to n minus 1 and over the indicator function. And let us assess what this term means. So we're taking the summation over all samples, and whenever a sample is e, then we have a 1 here and then we sum it up. And in all the other cases, there will be 0. So we are actually summing up all the times that our weather observation is e. So for instance, let's say e is cloudy. So we are summing up all the times the weather is cloudy. And we can call this shorthand NE for the number of times the weather is E. Well, this is a little abstract, but let's think of it as, for instance, cloudy, sunny, rainy, and so on. And then we can call this lambda is theta. Oh, surely, of course, this should be 1 over theta e. So then we have NE over theta e. And this is our first derivative. So let's now mark this as an important. Okay, then we take the derivative of L hat with respect to lambda. And if we do this, then we get our constraint. This is always like in Lagrange multipliers. If you take the derivative of the multiplier, then you get the constraint. But yeah, let's put this in, and this is theta d. Okay, let's just remind us what our actual goal was. Our actual goal was to find the theta e, and a common thing in Lagrange multipliers, or like the way to do like constraint optimization, is to get rid of the lambda, and that's our question here: how to get rid of the lambda. And we actually have to involve some sort of a trick. Okay, let us start with some true observations, and then we will get along and try to figure out what lambda is. So lambda is lambda. I think you would agree with me. And this then means that lambda is also lambda times 1, right? Okay. Well, what is 1? I mean, we know that the probabilities theta d have to sum up to 1. So I mean, this is like indirectly, this is also what is stated here. So that just repeat what we had before. This is nothing else as lambda times the summation from d0 to d minus 1 over theta d. And well, since lambda is a constant, we can just like put it into the summation here. And then we get the summation from d0 to capital D minus 1 over lambda times theta d. And if we then plug in lambda, we get the summation from d0 to capital D minus 1 over, and here we have ne over theta e times theta d. Okay, let us assess what this ratio actually means. So we have lambda is ne over theta e. And we said we look at one particular theta, and the lambda that corresponds to the entire optimization. So it corresponds to the e theta, to the e minus 1 theta, and the e plus 1 theta. So in other terms, it corresponds to the theta with respect to cloudy weather, rainy weather, and sunny weather. So in a sense, this is constant. And it also makes sense. The ratio of the number of observations of a certain weather state with respect to the probability of this weather state has to be constant. This then also means that we can take ne minus 1 over theta e minus 1, or also ne plus 1 over theta e plus 1. In case, of course, we're not running out of the bounds of our indices. But let's say, for instance, this was rainy. But we know that the same ratio also holds for the cloudy weather and for the sunny weather. And we can be really general about this and say this holds for any d, nd over theta d. And if we do this, say it holds for any d, then we can kind of cancel our theta d's in here. So let's try to do this. And then we get, so I will keep the lambda from there. Lambda is the summation from d0 to capital D minus 1 over nd over theta d times theta d. Then theta d cancels, and we are left with the summation from d0 to capital D minus 1 over nd. And nd is just the number of observations we have, rainy weather, cloudy weather, and so on. And we are summing over all possible states. So then this is just the total number of observations. And with this knowledge in our mind now, so like that lambda is this value, we can go back up. And we can go back up into what we had here. And based on this, we know that n is the ne over theta e. And if we rearrange this, then we get theta e is ne over n. And I think this makes a lot of sense. I mean, this is nothing else than the ratio of the times we observed this particular state of the weather with respect to the total number of observations of the weather. Okay, now let us check our derivations with an example in TensorFlow Probability. For this, I will open up an interactive Python session. Then I will first import a package in order to suppress TensorFlow warnings. Then we need TensorFlow itself. And we need TensorFlow Probability as TFP. Then we define some true theta values. We will only need them for creation of a dataset, and then we can ignore them because for the sake of maximum likelihood estimate, we assume we don't know them because we actually want to infer them from the data. So these are constants, so I will use TF constants in order to create a tensor. And let's say, for instance, 20% chance of cloudy weather, 30% of rainy, and 50% of sunny weather. Then we can create our weather random variable, which will be a distribution categorical, and it takes the probabilities according to the array we just created. And then we can create a data set by sampling the weather, let's say 100 times, observing the weather 100 times. And then we see, well, we have days with sunny weather, days with cloudy weather, and days with rainy weather. And now we want to build our maximum likelihood estimate, and for this we have to define the NE, the number of days a certain state occurs. And let's call this, for instance, n cloudy days. And for this we have to take the sum over the indicator function. So we do TF reduce sum over the data set being 0. So we check where is the data set 0, so because 0 is associated with cloudy weather. But if we do this, then TensorFlow will raise an error because if we do the equality, then it will output a boolean and we can't reduce the sum of a boolean. So we have to cast it, and we will cast the booleans into integers by saying tf.cast, and then we do dataset equals 0, and we cast it into an integer, and we use 64-bit long. And then we see how many cloudy days we have, and we have 21 cloudy days. Okay, let us just get over this once more. So dataset equals 0 returns a boolean array. Then we cast this boolean into an integer, and the array is 1 when we have cloudy weather and 0 if we have not cloudy weather, so when we either have sunny or rainy weather. And then we take the sum over it. And we can do the same for rainy weather, which will be n rainy. And we can do the same for n sunny. Let's maybe do this like this. But here we need, of course, change to 2. And then here, let's do the sunny. And we can check how many rainy days we have. We check how many sunny days we have. And this should add up to 100. And then we can find our theta's MLE to be, well, let's also make it a constant. And first we have to take the cloudy days and we divide it by 100 because we took 100 samples because our big N is 100. And then we have n rainy and divided by 100. And we have n sunny and divided by 100. Of course, in order to do such kind of an operation, we have to turn our value into NumPy values. I mean, this is a little overdone, but it should lead us to where we want to be. And we see our MLE observation is 0.21. And if we look at the 0.21, 0.28, and 0.51, and we see these are quite close. And again, as for all maximum likelihood estimates, they are off because the dataset, they are just derived by the dataset. And the dataset that we have is not fully representative for the entire distribution. And of course, you might also see here that the MLE is really not a robust estimate. I mean, we have a perfect dataset because we sampled our original model, but there is no noise inside of it. And by this, we see, well, we get close to it and we can infer these parameters, but always take the MLE with caution. Okay, I hope the derivation was clear and you learned something today. Here you will find more videos on similar topics. See you next time.